if you're not here for the thing. This information right here is for the review sheets. It not only has mine, but all the other SARC tutors and SI leaders review sessions and sheets and stuff on there. So this is my personal WordPress, as well as Valentina's. She's the other SARC tutor that I work with. So it has her and my information / study stuff on there. And this is the study union one. So if you have any other sessions you need to guys go to for any other classes, is where you're going to go. A few words, we are being live streamed. So please keep the voices down. The questions will be sort of at the end. It'll probably be like 20 minutes at the end where you guys can ask questions. So if you have them, just write them down, keep them down. I'm going to grab my calculator really quick because I just realized I don't have my calculator. But I'll be right back. All right, does everyone have a calculator with them? Something to do problems on? Cool. All right, so like I said earlier, this review sheet is available on this website, on both of these actually. It's just sort of chapters 1 through 10 stuff, what I thought maybe was interesting, and I've kind of grabbed from other SI leaders / tutors, because I know Elena, she's very good. She's been Zoran's SI for like 8 sessions or something like that, so she pretty much predicts what's on his test pretty well. I have a couple of questions in here for you guys in Zoran. Mackie, his tests are a little harder. It's more concept-based, but this, I think, covers a little bit of everything. So we're just going to sort of dive right in here. Can everyone read that in the back? It's hard. All right, let me. Is that better? Legible? All right, I'll read out the questions regardless, and then we'll talk about them. So the first part of this problem is determine the magnitude of the projected component of the 100-pound force acting along the axis BC of the pipe. So what we want to do here is we see, okay, what's important in this question? So we need the magnitude, right? So it's not a vector, it's going to be a scalar, of the projected component. So we need a projection of a component, which is usually a force dotted with some unit vector in the direction that you're looking for the projection of. So it says acting along the axis BC, so that's going to be the unit vector that we're going to use. But first let me located. Looks like, let's see, -3, right, because we go 3 feet back in the x-axis. And then we'll do 0 in the y and 0 in the z as well. And point right at the origin, so points are 0, 0, 0. It's out along the x 6 feet, and then out 4 feet, and then this is the y. All right, and then we have one more point D. All right, and D's all the way out here at 0, 12, 0. Right, so I write all these points down just so we have something that we can, when we need. And if you need to move this, if I somehow I'm over here and you need to see what's over there, just sort of raise your hand a little bit and then point to the board. Don't really say anything. I'll know what to do. All right. So the first thing we want to do is get our directions, right? So we're going to be making vectors for things. So I'm going to look at C to B because I know that this is the axis of the pipe, or this is the axis along which we're trying to find the force. So, right, so if B is the second letter, then I'm going to subtract. So I go 0 minus 6, so that'd be -6. And then I go 0 minus 4, -4. And then I go 0 minus -2, so that's positive 2. Right, so I have my CB. And now, if I want to find the unit vector, which I need to find the projection, I'm going to want to take CB, which is equal to -6 squared plus plus 2 squared. All that is equal to, I'm going to leave it like this, to be square root of 56. I don't want to deal with that decimal right now, so we're just going to leave it like that. So let me, vector is vector magnitude, right? X, Y, and Z components by the magnitude. So over square root 56. Now we'll go negative 4 over square root 56, and then 2. Okay, so now I need another direction. I need the direction along which this force is moving. So that's from C to D, right? So C to D, we go D minus C, would be negative 6. We go 12 minus 4, which is 8. 0 minus negative 2, which is 2. Okay, and so now I need to do the same thing, find the magnitude. It should be negative 6 squared plus 8 squared plus 2 squared, which is, again, leaving it in square root form so I don't have to deal with it, root 104. All right, so the whole idea is that we're going to want to find the force CD, the components of it, x, y, z, and then we're going to want to dot it with whatever unit vector we're looking to find the force along. In this case, it's the axis BC. So it would be the BC, or in this case, CD. And so now I can find the unit vector, right? Because this is where the force is moving, C to D. So that's why I'm finding unit vector C to D. So I get negative 6 over root 104, 8 over root 104, and is it 2 over root 104. And I'm going to have this posted online today, because I know some of you tomorrow, so you probably want it as soon as possible. All right, so now what they tell us the magnitude of the force is 100 pounds, right? Magnitude. That means scalar, not a vector. So we need to find the vector. So that's why we're going to dot it with this unit vector CD, because that's the direction of the force. So the force, they tell me, is, right, this is the magnitude, is 100 pounds. So I'm going to multiply it, I'm going to dot it with unit vector CD. And I'm going to get negative 600 over root 104, right, because I'm just multiplying 100 by each of these terms. 100 over 104, and then 200 over 104. So I'm going to run off the page here, but as long as you guys have the stuff, I'm going to try to like go up and down sort of horizontally, or vertically rather. So all right, so now this is my force vector, right? This is force CD, and I'm going to write a little arrow above it to denote that it's a vector. All right, not a scalar. So now I need the projection. So there's two things you can get. You can get a component, or you can get a projection. And so without getting too calculated, the component is basically, right, so this would be component. Component is basically just what we did there. We found the component of force along that CD axis. Now the projection would be, oh, and you do this with x and y. I don't know if maybe unknowingly, but like to find like the x component of a force or the y component using sine or cosine, that's component. Dotted with a unit vector. So both of these, so this gives me a scalar, right? I don't know what it is, but it'll give me a scalar because that's how they work. And then here I'm going to have, so let's do that down here. So I'm going to say the projection of a force CD on the unit vector BC is, and then I'll write it out for you guys. So over 104 times negative 6 over 56, right? So I'm, yeah, no, this times this, and then this times this, and so on. Can you guys see everything? Good? All right. All right, so this is my first term. times negative 4 over 56. And 200 over 4 times 2 over 56. All right, so add all this up, get 10.48 pounds. Okay, so like I said earlier, we're going to try to keep the questions to a minimum, but I appreciate it. So I dotted with, so I said the projection of force CD dotted with the unit vector BC. I'm trying to get along this axis here, or I guess CB in my case. I did CB. All right, so that's what I found up here, and I dotted it with to get this component here. All right, so now we're going to do the second part of the problem. So the second part of the problem says, determine the angle between pipe segments BA and BC. So angle. When we have angle and we have two vectors, we're going to want to use dot product. So maybe let's do this. We can actually fit this in down here. Space. So we have our points from up here. So I'm just going to say vector BA looks negative 3, 0, 0. And BC is 6, 4, negative 2. Right, and so now a part of the formula for dot product is two vectors dotted with each other is equal to the magnitude of those two vectors times the cosine of the angle between them. So what I'm looking for is I need BA dot will be equal to the magnitude of those vectors multiplied by each other times cosine theta. And I'm sorry if my voice fails me sometimes, guys. I was at the game yesterday and I was doing a lot of cheering. So I need these vectors here, and I also need their magnitudes. I found the vectors, now I need to find the magnitudes. And then I can use inverse cosine to find this theta. So the magnitude of BA, right, 3 squared, square root of 3, 3. And then would be equal. We did that up here, right? We got root 56. So I'm just going to write here. I'm going to move over the cosine. So I'm going to say cosine of theta, and then I'm going to move over these vectors. So I'm going to do negative 3, 0, 0, right, because that's BA, dotted with 6, negative 2. That's B. Right, and then I do inverse cosine to find my theta, and I get 143.3. All right, so there are my two answers. Like I said before, magnitude of the projected component, and then determine the angle between them. Whenever you see angle between two vectors, you're going to want to use dot product. All right, and then if it asks you for magnitude, you know that means scalar, right? Magnitude, scalar. Okay, so if you end up with a vector, you did something wrong. All right, so let's move on to the next problem. Next problem is chapter 3. So we're still dealing with forces and vectors. In this case, it would be still three-dimensional space. But this one I thought was kind of cool. I don't know if everyone can see. Maybe I'll zoom in a little more. So it says, determine the stretch in each of the two springs required to hold the 20-kilogram crate in equilibrium position. So that's what we're dealing with in statics most of the time, or all of the time, rather, is equilibrium. So each spring has an unstretched length of 2 meters and a stiffness of K is equal to 360 Newton per meter. So just really quick, the equation to find the force in a spring is equal to some spring constant times some change in X. So if it has a natural state of where it likes to stay, if you elongate it or compress it, that delta X multiplied by your K value will give you the amount of force required to move it, or when you compress it, the amount of force that it's going to expend to get back to its equilibrium position. So that's just something to keep in mind. All right, so let's do what we did before in the last problem. Let's just write out our points again. I'm sure everyone can see that. So O is my origin point, so it's going to be 0, 0, 0. And then I have A, 0, negative 4, 0. B, going to be negative 6, 0, 0. So the x-axis. You guys can z. And then here. So I'll zoom it out once we've talked about the problem. That way all my work sort of fits. All right. And C. So 4, 6, 12. All right, so I want to find, I don't know the forces in each of these supporting ropes, right? So I want to find their position vectors. And so, so that way I can compare them with some force equation and then solve with unknowns. So O to A, right, would be 0, negative 4, 0. O to B, negative 6, 0, 0. O to C, 4, 6, 12. All right, because they're all from the origin, so they pretty much at the point. So, so what I want to do now, like I said, is find these positions. So when I have them all converging to one point, and I have a weight connected to that one point, they're each going to provide their own x, y, z components of force. In this case, we can see that A is lying only along the y-axis, and B is lying only along the x-axis, while C has all three components. So we're starting to get an idea about which equations we're going to use. So if we unit vector quick, so the unit vector of O to C would look like 4, 6, 12 over the magnitude of 4 squared plus 6, 12, that. And I've already done this math, so I'll just write it out. 3 over 7, 6 over 7. Vectors are important in case you don't know because they show direction. So right, so I'm going to say a hypothetical force, right, I don't know what it is, but I can put a little folder variable, FO, because I denoted it with this arrow notation. Here, it does not have an arrow notation. And then so I'm going to multiply that by the unit vector that I got here. So what this is going to do is going to set up forces in the x, y, and z, and then solve based on that. And then solve which one has at least done first. So now I'm going to go to unit vector O to B, and it's going to be negative 6, 0, 0. And then square multiplied it. I'll do it again. Right, because it's 6 squared, square root of that, 6. So I have negative 1, 0, 0. Okay? Because remember we said earlier this one was only lying in the x-plane, right? That's B. It's only lying in the x-plane, so that makes sense that our unit vector is just negative 1 in the x. Variable saying the vector of force is equal to the magnitude times the unit vector. Okay. So now I have sort of right. So 0, negative 4, 0 over negative 4 squared. Said that earlier, it only lies in the y-plane, so that makes sense. And statics is kind of all about checking yourself to make sure that what you see lines up with what you already know. So if I had gotten something different than negative 1 in the y, I would have been, okay, I did something wrong in my vectors up here, so I got to go back and change it. But everything looks good right now. All right, so my last dummy variable, dotted with 0, negative 1, 0. So yeah, these sort of convey the component of the force along these ropes, right? So I know that these three ropes are what's holding this weight up. So that's why I've created sort of three equations. So now I can say, I can use my sum force equations. So right, I can x, y, and z. The vector plus the force vector. Assume they're all positive, because we do that a lot in statics. use the tension say. So, and I see as a k value, right? So it's going along the z-axis, the negative z-axis. So the right, and it's negative because weight is coming down, and that's mg. Do they tell us? Yes. So we have m, right? M is equal to this 20 kilograms here. So my equation is going to get a little more complicated. But now, so sort of to get a general idea about what I'm going to do. So I can split this into x, y, and z, and I can say, okay, components are, so some of the forces in the x has to be equal to 0. Say, what are my components of my x? Here, I have an x component. Here, I have an x component. Here, I don't. All right, so I'm working with two variables here. That's equal to negative FOB, right? FOB times negative. And then plus 2/7. I notice some of you may be recording this or streaming it. It is available online, like on YouTube, I believe, and there should be a link somewhere. So if you want to get maybe a little higher quality recording, it'll be available there. And for all you guys watching, you already know that. So, all right, so I have two variables. Solve that if I have one equation. There you go. Thank you. So now, sum force y. So I'm just going to run through all my sum force equations and then solve them there. So that's what I like. In statics, you always want to go with you always want to solve what has the least unknowns first, and that'll slowly. So here I have negative FOA. That comes right here, because we're dealing in the y, right? And then I'm going to have plus 3/7 FOC. Came over here. Two unknowns. All right, so now I'm going to go with z. I know that's equal to 0. And that's going to be equal to 6/7 FOC. And the other z component I have, right? Because I have one here, this FOC. I don't have one here. You have that mgk. Right, so it's 20 times the constant for gravity, dealing in SI, so it's going to be 9.81 meters per second. And then, so that's 196.2 newtons. I have one unknown and an equation and a constant, so I can solve this one. So, and so on. So that's the whole idea. This is FOA is equal to, we can plug it. Change my equation. Solve. Now, the question asks, up here, it says, determine the stretch in each of the springs, right? So we said earlier that our equation for our spring and our force was force is equal to k delta x. So what we just found was F. What we have here is k, so now we can find delta x. So a little thing here. Let me solve. And so I can say delta x of OA is equal to the force of OA over my k value. And like I said earlier, my k value is equal to 360 newtons per meter. So, so that comes out to 98.1 over 360. And so delta x OA is equal to 0.2725 meters. Okay, and that makes sense. It's not a huge amount. It's also not a very, very minuscule amount. So if you have numbers that are, 10 to the 3, it's probably not the right answer. Likewise, 10 to the negative 3. So that's just, realizing what your bounds are and what dimensions you're working with. So now we have delta x OB, right, which is equal to the force OB over K, which in this case is the 65.4 newtons over 360. And we have newtons over newtons per meter, so we should get meter out. Delta x OB is equal to 0.1817 meters. And if your teacher prefers significant figures, do it that way. I just like to keep things in as many decimals as I can in case I need to use them later. And then finally, so finally it asks for delta x OC. So we have force OC over K equal to 228.9 over, our K value is 360. I actually haven't done this one, so let me calculate it really quick. 360. So we have delta x OC is equal to 0.6358. Okay? So the thought process behind this one, my question said determine the stretch in each of the springs. I know that stretch and spring is modeled by this equation here. They gave us a mass of this object, and they said it's in equilibrium, right? So our sum force equations apply. So each spring has an unstretched length of 2 meters, and a stiffness of K is equal to 360 Newton per meter. So what we did was we found our directional vectors and our unit vectors, and we plugged in a dummy variable so that we could then solve our sum force equations in terms of variables, and then get actual values, and then plug them back into our equation. All right? Cool. So I'm going to move on. Like I said earlier, there will be a 5-10 minute break, probably about 5:30, so halfway through the session. And then the last 15-20 minutes will be relegated to questions / things that I think might be important for you guys to know. All right, so this is a moment problem about, about a specific axis. But I sort of want to get a feeling, because we don't have a whole lot of time. It may seem like 2 hours, it's a lot, but when we have to explain a problem all the way through, it can take some time. So I want to see if maybe we want to move on to the later chapters. So if you guys maybe think you want to see stuff like chapters 6, 7, 8, 9, 10, raise a half hand so you don't block the monitor. All right, yeah, because this stuff is basically just unit vectors and finding moments, but I'll go through how to solve it. I won't necessarily go through the entire process, just so you guys know. And then we'll get into maybe like some truss problems, some method of sections. And then I have like a shear moment diagram here, friction, and moment of inertia. All right, so we'll do that. All right. So the idea here is the pipe. All right, so let me zoom in for the question. Pipe assembly is secured on the wall by 2 brackets. If the pot has a weight of 50 pounds, now they say weight, right? Weight, we know, is different than mass, because weight is multiplied by the force of gravity. So this right here is a force, right? So that's just something to keep in mind. Determine the magnitude of the moment produced by the weight about the OA axis, right? So moment is force times the distance, right? It's work. So what I'm going to want to be doing is I'm going to want to find the moment OA, and that's going to be equal to the unit vector OA dotted with some moment that I find about the origin, right? Because that's my center point. So this is important because we can find a moment, and then we can find the magnitude of it along a specific axis by dotting it with that unit vector's axis, or the axis's unit vector, rather. So that's basically what I'm going to be doing here. I'll mark all my points, find my vector OA, find my unit vector OA, and then, so I have a force here, and I'm going to say, I'm going to use my, my matrices, right? You guys, I assume, know how to use matrices, but if you don't, really quick, it's going to look something like this. It's going to usually be like a 3x3. We're going to have an I, J, and a K. And then let's just say force 1, force 2, force 3. And then, actually, usually, I'm sorry, let me correct this. Usually, right, I said moment is force times the distance, so it'll be R cross F. That's important because your R's are going to be on the top and your F's are going to be on the bottom. Right? And so if you mess up this order, you're going to get a negative value, which is going to be incorrect. So it's important to remember your order here, R cross F. And so what I'm going to be doing then is MOA is equal to ROA crossed with my F. In this case, my forces is potted plant. And then I'm going to dot all that by a unit vector. So I cross product to get a vector, and then I dot two vectors to get a scalar. So that's why they ask here. They say magnitude, so I know I need a scalar. That's how I know that this process is going to be correct. All right, and then the second part of the problem says the pipe assembly is secured on the wall by two brackets. If the frictional force of both brackets can resist a maximum moment of 150. So they've given us our end condition. So they've given us what we found for in the previous problem. It says determine the largest weight of the flower pot. So now we need to use moment, position, and then define force. Okay? So that's all we're going to be doing. So this equation that we got earlier, we're basically going to be that value that they give us, which is 150. So it's going to basically be 150 equal to ROA cross F supported by O. Right? What we're going to have. So we're going to for the F in this case. Right here, we're solving for the moment. We're solving for the F. All right, so that's basically how we would solve this problem. It's not too difficult. There's not too many things you need to compute. Only thing I would say is when we're figuring out our angles between our component and our axes, we need, if we're using angles in the x and y, like here we have 60 degrees here. This is in the xy plane, that's 60 degrees. So if we want to deal with this portion of B right here, we need to get it down into the xy plane, and then we can use our angles that we're given. We can't just straight away say that's multiply cosine 60 degrees will give me x. So just an idea, I would need to do, if I wanted to get the component of this along the x-axis, I would need to do, let's say, B cos 30, right? Because I'm going for this component here, which lies in the xy plane, and then I can deal with it, right? And then I can multiply it by cos 60. So this is one of the problems you've seen where they give you maybe something like sort of separated by a weird angle, right? 90 degrees, so you can't deal with them like x, y. So you use the law of sine. You have to use projection components to figure out your values. So that's just, from there you'll get a maximum weight, right? Weight max. Because then you'll get a force divided by gravity, or no, force is a weight rather. So that would just be the value. All right, so we're going to move on since everyone kind of wants to get to the good stuff. So chapter 6. So this is where we start dealing with method of actions and method of joints. So any problem, and I want to say problem, maybe 99% can be solved using method of joints. The problem is it's very time consuming. For example, if we count here how many joints I have, it's 1, 2, 3, 4, 5, 6, 7. That's 7 different systems of equations we need to solve, not just 7 different equations. So that's going to take us a while. So we need to figure out what we want to do. But the question here asks, determine the force in members FG. So I'm going to highlight the members as they call them. FG, right, it's that one there. GC, it's this one here, and then CB. And it says, if they're used to support the sign, and state if the members are in tension or compression. So just a really quick note. Tension, I wrote it up here. Tension is something that we normally assume. It's positive, right? So that's when you have a point here and you assume that all the forces are leaving, right? It's being pulled outward. That's what we assume as tension. Compression is the opposite. It's negative, right? That's when we assume everything to be going into a point. Right, if these are all in compression, then they're all going in, right? You're getting compressed in, you're getting pushed. All right, so the first thing we want to do in most truss problems is identify any zero force members. So something key that we want to look for that will tell us right away if we have a zero force member is sort of this little thing right here. So it's collinear forces, right? So if we have two members meeting and we have a third that splits orthogonal to them, we know that, like for example, this, if we do our sum force equations in x, let's say this is A, B, C, and this is O, I know it has to be equal to 0, right? So I can say FOA minus FOB is equal to 0. So that's fine. As long as FOA and FOB have values, then this won't be 0. Nothing's a problem here. The problem arises when we get FY, right? Because B and A have no components in the y-axis, so now we're just going to get FOC is equal to 0. So that member right there is equal to 0, right? So that would be a zero force member. So here we look and we see at E, do we have a zero force member? So we have an X force, and we have an X component to this member here. So it's not looking like we're going to have a zero force member. It also has a Y component, which complements this. Same thing with D and C, right? They have an X component and a Y component, X component, Y component, X, Y. So it looks like right here we don't have any zero force members, so that's good. So that's the first thing you want to do. So zero, let me not slant this, force members. That's something you always want to ask yourself. In this case, it's no. So now we can get on with our problem. So like I said earlier, we could do method of joints, but that would take a very long time. So what I'm going to do is method of sections. So it's basically making a cut. So I want to find the best place to make a cut, right? And keeping in mind that I don't want more than 3 cuts, three members cut, because I only have 3 equations that deal with unknowns. So if I have 3 equations, theoretically I can't solve. So in this case, I want to make a cut, and I want to cut through the object, right? So these 3, 1, 2, 3, are sort of in line with each other. So if I just cut right through them, I'll end up with forces, you know, I'll label them as forces coming out. And that's exactly what I have to solve for, so that's what I'm going to do. The cool thing about method of sections is I can also decide what side I want to look at. So do I want to look at this top part, or do I want to look at this bottom part? Well, I don't really have the support values for A and B, and I'd have to I could do it, I could calculate them, but that would take extra time. And on your exams, you're going to be sort of crunched for time. So here I want to look at the top, because all I have are these external forces here, and then the unknown forces that I'm going to have there. So that's what I'm going to do. So I'm going to draw my free body diagram. Let me zoom out a little bit. Please, please. All right. Free body diagram. So start at point E, come down. It's got some force pushing on it, 900 newtons. This is D. And a force here. This is where I cut, right? We make them forces. This is F. This is E. This is C, right? So these two have forces pushing in on them. Looks like 1,800. This is 900. All right. And then I'm going to label this FG, right? Because out here is some imaginary point G. Just because we cut it doesn't mean that it's still not there. We can still use it, and we will. And so I'll show you how. CG. All right, so I made a cut, and I turned them into forces. So now what I can do is I can apply my equations, my equilibrium equations. So I look here and I say, okay, if I want to do some force in the x, looks like I'm going to have 2 unknowns, right? Because FG is going to have something in the x and the y, and then CG is only going to have in the x. So I'm going to have 2 unknowns, 1 equation. Maybe I can look for something else. All right, let me finish. I didn't label any distances that might help you guys out. So that's 1.5 meters. And then from here to here, 3 meters, 3 meters. Cool. So, all right, what about some force in the y? So I have, again, we run into the same problem. I have a force here in the y, and this has also a component in the y. So that will give me 2 unknowns. And they won't be the same 2 as the other, so I'll have to have another equation. And what's my last equation? My moment equation. So I want to find a point by which I can take a moment. So the cool thing about this problem is everything here can be solved using a moment, about a point that is either on or off of the truss. So I'm going to say I want to take the moment. I could take the moment about point C, right? Because then I'd get rid of these 2 unknowns because they have no distance away from that point. So there is no moment created. And I can just find this, right? So I'd have all these other values. I'd have these 2 to deal with, and then this 1 value. So that's 1 unknown, 1 equation I can solve. I could also make a moment about point G, because I have these two forces coming in at point G, and then this one leaving, right? This one has some distance away from G, and then I have some unknowns here. So I'd have one unknown I can solve. And then my last point I could say about F, right? Because once I solve the other two, I'll presumably have one or both of these, or I'll have one of them, and then I can use moment about F to solve for the other one. So let's start with the one that has one unknown. We'll do the moment about C. I'm sorry if that was a mouthful, but I'll go over it again as I'm talking. So I do the moment about C, right, and I have to specify my positive direction. And I like to say right-hand rule convention says that counterclockwise is my positive direction. So moment about C is equal to 0. Actually, we'll do G first. I'm sorry. G, because you don't have to use a triangle to solve for that yet. So this point, imaginary point out here, it still matters. Just because we cut it doesn't mean it doesn't matter. It still has feelings. So we're going to take the moment about point G, because these two converge, and we'll be able to find CB. So this 900 newtons comes in at G. There is no perpendicular distance between the axis and my moment, right? It just continues the line. There's no moment created. So I don't consider this a moment equation. Now when I have this this force right here, this 1800, there is some distance, right? There is some, because this force acts along this axis here. So there is some distance there, and that distance is 3 meters. So I'm going to say, and is it positive or negative, right? So if I hold the point, and this I'm going to keep stationary, but if I hold the point at which I'm finding my force about, if I push in the direction, it looks like my paper is turning counterclockwise. So that means I'm going to have a positive value. So it's going to be positive 1800 newtons times 3 meters, right? Because that's the distance from here to here, because that acts along that line. And then what else do I have? I have this external force here, 900, and it does the same thing, right? If I push along that way, it's also counterclockwise. So I'm going to add 900 times, and that distance is 6, right? It's 3 plus 3. And then what else do I have? I have the thing that I'm looking for, CB. Now when I push around CB, it turns the other way. It turns clockwise, which is my negative value, or my negative direction. So I'm going to say minus CB times the distance, right? My distance here is what? So from G to C, 1.5 to F, and then 1.5 again. So my distance there is 3 meters. So I'm going to have 3, and that's equal to 0. Okay? All right, so now I have one unknown in my equation, so I can solve. So I say, therefore, I can work with that. CB is equal to 3,600 newtons. And I got a positive value, right? Because if I move this over, everything will be positive. I got a positive value, so that tells me that it's this number in tension, right? So I can just write that. 3,600 newtons in tension, because it asks tension or compression. So next, I said we can find the moment about C, because that gets rid of these two unknowns, right? So I can find FG. So to solve for C, I need to make a little triangle, but we'll do that when we have to. So some of the moments about C, again, positive convention. And so what do I have? I have this force FG. Now, I don't really know the distance between C and F, and actually there's a member connecting them that I sort of forgot to draw, right? It's that one. So if I could find this distance here, I could be able to multiply it by that force to get the moment. So I make my little triangle, right, FDC. And then I say, I know that's 1.5, right, because they give that to me up here. And I know that's 3. So if I do a little Pythagorean theorem, it's about 3.354. All right, and you guys can check that on a calculator. Should be correct. So I'm going to find, so now I'm going to do my moment, right? So in this case, FG, about point C, spins me, what direction is this? This looks like counterclockwise, so that's my positive direction. So I'm going to have FG, positive, times the distance, right, from F to C, 3.354 meters. And then this 1800 is also going to give me counterclockwise, all right, as well as this 900. So already I'm starting to see something here. All my values that I have for them, for my knowns, are positive. So that tells me something. That tells me that whatever my unknown is going to be negative. All right, and we'll see that. Right, so you move G over, it becomes negative. And then we find that Fg is equal to 3,219.94 newtons. And it's a negative value, but instead of putting a negative in front of it, I'll just say in compression. Right, because it's like a magnitude and then the state, right? So the magnitude, state, magnitude, state. Okay? So my last thing I need to find, right? I found CB, that's good. I found FG, that's good. Now I need to find CG. So I could use some force X, Y. I could use a moment. It's honestly whatever I want because I only have one unknown. And so I'm going to use a moment just to keep in tradition with the rest of the problem. The moment about point F is equal to 0, right? So this point right here. And so there's these two unknowns, right? I couldn't use this earlier because these were both unknowns. Now I have CB. So now CG is my only unknown, and FG is not going to be included because it's along that axis. And then I'll have some external forces here. So is equal to 0. And so off a negative 900 meters. I should like mark this table so I see where the top and bottom. 900. And then I'm going to look at my force CG, right? And I say that the same distance away and in the same direction, right? So I'm going to also negative CG times 3 meters. Last, it's 8 on the axis of in the moment, so it's not going to cause a moment. I have another force, and that's going to bring what kind of rotation? Looks like counterclockwise. So that's going to be a positive value. So I finally have a positive 3 meters, and that's equal to 0. And is that it? No. There's one more thing, which we solved for earlier, right? The CB brings me down. It moves clockwise, so it's negative. Some negative CB. No, we already have CB, so I'll just plug it in there. I just like having everything sort of denoted. And then I just plug in whatever I have. So that's all equal to 0. Negative value we know are in compression. Right, so we saw what members we had to we needed to find the forces of. We cut through all 3 of them. It was a very fortuitous cut, which gave us these 3 forces in our free body diagram. And then we just used moments about various points to find our values. Cool. So after this problem, I think we'll take a little bit of a break of shear moment. All right, so this is meat and potatoes of solid mechanics. It's a fun class. So I have little conceptual questions here. How does the normal force of the cable contribute to the shear? Right. So the normal force of the cable would be here, right? It's this force here. So if we have, all right, so our this. Positive. Positive. All right, so if I'm coming over here, and this is my beginning point, I'll have a force coming down here, and it's going to be going, and so this would be my start point. So I have a force coming down here, so that would be a positive value. So we'll see that. So we'll answer these conceptual questions once we're done solving the problem, but just think about them. All right, so let me zoom out a little bit. All right, so there's sort of a couple ways we can solve this. The more complicated shear moment diagrams, you will need to use your equations. In other words, just initial moment. These are derivatives of each other, right? So shear is the derivative of moment, and then distributed load is the derivative of the shear in this case. So here we have a distributed load. So we could use this method to find the shear. So an equation for the shear, rather. So what we want to do is we want to break this into sections. So what I like to do is I like to draw a little free body diagram on the side. Right, this is my beam up here. And I'll say that there's some distributed load, right, to there. There's also some force at B equal to 500. And then there's some force at C, which is sort of angled, right? And they give us the dimensions, 3, and then this is 4, so that's going to be a 3, 4, 5 triangle, which is a fairly common one. So 3, 4, 5, and that's FC. Right, and then so A, it looks like it's a pin support, so we're going to have a horizontal, we're going to have a normal and a axial, I guess, support. So AY and AX. Okay, and so we don't have a support over here, we just have this force that we've labeled, right, because this goes all the way up to here, so we'll just label it as a force for now. And then we have our distances, right, so that's 2 meters, and that's 2 meters. All right, so I've drawn my little free body diagram, excuse me. So now I draw below it, I draw these lines, and this is where I'm going to have my, my shear, my moment. I just like to draw them below each other because, like I said earlier, they're integrals of each other. So the area will tell us something about the slope of the integral. So in this case, it's going to be my shear, be my moment. And I'm going to need to separate this, right, because I need to look at it in sections. So I see a point where my distributed load ends. And so if you have a point of force or a point where a distributed load ends or begins, you're going to want to sort of section it off. Right, so I'll do that with this dotted line here. Right, it runs all the way down. Sorry if you couldn't see that before. All right, so that's what that looks like. So now I need to solve for my support reactions, because that's usually what you want to do in most cases, only really when you have to. In the last problem, we didn't have to solve for the support reactions. We used the upper half of the truss, but in this case, we need to solve for the support reactions because they're involved in the shear here in the moment. Right, so really quick, what is the resultant force of this distributed load? It's 250. And we have a base, it's 2 meters. All right, so I can say that's equal to 500 newtons. All right, and where would that be concentrated? At the centroid of this shape. Because it's a rectangle, the centroid is going to be located at half the base, right? 1/2 base. And the y will 1/2 height, but we don't have to worry about that because this y is sort of imaginary, right? It's not a real rectangle, but it's just easier to model our force like that. Okay, so that's where our force is going to be acting. So we need to find our support reactions. So what I want to do first is find this C, because once I have C, I can then use the sum force equation to find my A. So I'm going to take the moment about A, right, and I'm going to positive convention equal to 0. So I say force would bring, looks like counterclockwise, so this force, and I'm looking for, this force at C has 2 components to it, right? We have a little triangle here. It's got this X, and it's got this Y rather, and this X. So the X component will not cause any moment about A, but the Y component will. So that's what we're going to be dealing with. So we need to find the Y component of FC. We don't really know FC, but that's what we're trying to find right now. So but we already have the size. We're just going to multiply. Right, so that's my force. So I need a distance, 2 and 2. Positive, because it brings counterclockwise. So now we have this 500 Newton force, and that brings me clockwise, and that's going to be negative. And 2 meters. And then I have this also this distributed 500 Newton load, right? And I said it's half of the base. Sorry if this runs over. All right, and I know. Okay, so solving this, I find FC is equal to 625, right? So you keep in mind. Now that we have FC, it has an x and y component, as I said earlier, so we can use our some force in the x, some force in the y, and we only have one unknown, which is what we're looking for. So some force in the y, and I'll say up is positive. You can say down is positive in some cases if it makes your life easier. Just be sure to denote it on the side. 0. So I have forces. AY force. I have this distributed load force, this force here, and then a y component of this force, right? So my AY is positive. Assuming it's positive. I like to assume support reactions are in the positive direction. Distributed load is down, so minus 500. I have some force C, right? And it looks like it's pointing up. So I say up 625, right? Force the y component, right? 3. And we know that's equal to 0. Okay. So that y forces I see equal to 625. And I just boxed it in because it's kind of important. And then the x forces aren't really that important here. They don't ask us about normal force, right? They ask us for shear and moment. So like I said earlier, these normal forces, they're not really too important. AX and FC has an x component, but don't waste your time here if you don't need to, because on the test you're not going to have a lot of time. And I recommend if you're trying to do these problems, maybe tomorrow again, after you sort of forget things, try to do them within 15, 20 minutes, because that's all you're really going to have on the test. All right, so back here, I say, all right, so now I y, right? And that's important because that's going to give me my initial value for my shear. So going back to this equation, there's some initial value, right? Because when you integrate, you get some constant C. So that's what this constant is taking into advantage. It's this initial shear. So in this case, I have an initial, as soon, like this is negative space, right? These are my x axes. As soon as I get to A, I have some initial shear, initial force, right? And that's equal to AY. So I can say, right, that no, it's terrible. But that's equal to 625 newtons. Right? Good. So let's see. So next, I say, okay, like I said earlier, there are two ways to do this, the equation method and the area method. I will do the area method in the interest of time, but on my solutions, I will also do the integral method. So, so here I have an area, right? And I see this, I'm evaluating this area, and I say there's a negative force inside, right? Because it's coming down, right? So it's a negative force, and it sort of maintains its area all through here, right? The height doesn't change. You know, if I took some differentials, a bunch of differentials, the area doesn't really change, right? So I can say that this area here is constant and negative, right? The force is negative, and the area is constant. So it's negative and constant. So that means the slope of my integrated function, in this case shear, is going to be negative and constant as well. But how much, right? What is my slope? In this case, they say that 250 newtons per meter is W of x. Right, I'm integrating W of x here, so that's going to be my slope. So I'm going to be coming down at a rate of 250 newtons per meter. Right, so here I have 2 meters. So I know that after 2 meters, I'm going to fall a total of 500 newtons. Okay, so I'm going to come here, and I'm going to say, coming down, boom. So I know that final here equal to my initial 625 minus W of x times my distance, which is 500. So this will give me 125. Right, and then right as I get really, really close to B, all of a sudden I have some downward force again. So I need to take that into consideration. So I come down, and I bring it down, right, along B. And so that would be equal to 125 minus 500, right? So in this case, I end up at negative 375. Okay, so let me shade in this little area here. All right, and so what else do I have? So in this section, I don't have a distributed load. I don't really have a force until I get to the end. shoot up. I shoot up at some value equal to the FC, the y component of FC. Well, the y component of FC is equal to 625 times 3 over 5. And what is that? Just 375, right? So we take this negative 375, we bring it right back up to 0. And that's where we should end. We should end at 0. Okay? So this is my other area. All right, and that's this FCY brings us back up to 0 at the end. All right, so now I'm looking at the area again, right? So kind of forget this top part. And I say, what is this area doing? Well, this area is positive, right? This force is positive. It's because it's above this x-axis. And it looks like it's getting smaller, right? It's decreasing. So what do I have? I'll make that bigger. Sort of neglect infants, right? Dumb people instead. So what this means is if your area is positive and decreasing, then the integrated slope is going to look something like this. All right? So that's the case we have here. We have a positive and decreasing area, right? Because the area is getting smaller, but it's still above the x-axis. So positive and decreasing. So we're going to start down here, and we're going to come up to some value here. All right? And another important thing about the relationship between integrals and derivatives is that if we have a 0 in our derivative, then we're going to have a maximum or a minimum in our integrated function. So in this case, our shear crosses 0 at point B, which tells me we're either going to have a maximum or a minimum at point B. Well, I can see here, based on my slope, it looks like we're going to have a maximum, right? Because it's coming up here, because 0 looks like our minimum. So now what I do is I make a little cut at B. So I want to find the moment about B, right? So the sum of the moments about B is equal to 0. Okay? So include the moment at B. It's not a support, so and like early, like we might have a couple moment, but we're not dealing with that yet. So there is some moment when I cut. So that's what we're for now. If we get a negative value, then we can say it's negative. And then what else do we have? So I'll make a little drawing. So I'm going to look at the right side. You can look at the left side since we found the supports. But whenever you make your cuts, you decide, right? Same thing with method of sections. So I'm going to look at the right side. Right, up here. And then there's nothing. There's just 2 meters of nothingness. And then we get our positive, right? Because this is our positive convention. We get our positive shear. Normal doesn't really matter. Sorry, normal, you don't really matter right now. So I'm going to take about worrying about is the y component, right? Because the x component, this bar is really thin. So some professors like to give you the thickness of this bar. If you're taking from the exact center, you're going to have some moment created by the x component. But for this course, we consider these bars to be infinitely thin unless otherwise stated. So that's why the x component doesn't have a moment, doesn't create a moment. And if that sort of doesn't make sense, then I can ask me a question about it later. Here, of course, so 3 over 5 again, times FC. 150 Newton per meter. Right, my maximum because it's a 0 in my derivative function. And so over here we also have a 0. So we're either going to have a maximum or a minimum, but if we already have a maximum, then it's got to be a minimum, right? So we're going to end up back at 0 again. But now I can say that this here, able that I can say this peak point right here is 750 newtons per meter. So again, I'm going to look at this area. So from here to here, this area is negative, and it's not really changing, right? It's negative because it's below the x-axis, but it's constant, right? It's a constant negative area. So what that tells me is my slope of my integrated function is going to be constant and negative. So I know just based on experience that it's going to come to 0. but we can evaluate that mathematically. So this is my area. All right, so if you take the moment about point C, you'll find that, well, the sum of the moments about point C is equal to 0, which is why we end up at 0. The only time that it wouldn't end at 0 is if maybe, let's say, they had given you some final moment here, moment C. Then whatever your value would be included in this diagram, right? You'd have to include that moment at C, but it's usually going to end at that 0 because we're statics, that's equilibrium, no acceleration, so we're going to end up at 0 in equilibrium. All right, so we're going back to our conceptual questions. So we did the shear moment diagrams here. How does the normal force of the cable contribute to the shear? So the cable, if we look based on our diagrams, the cable brings it up, right? So does it increase the shear? Does it decrease the shear? So in our case, it brings it from a negative 375 to 0. So you might want to say, okay, it increases it, negative to positive. But shear, in this case, we're dealing with is an absolute value, right? So if I'd asked you for the maximum shear, it would be 375, right? It doesn't have to be a positive or negative value. It just has to be an absolute value. So the absolute, just like the absolute moment is 750, the absolute largest shear would be 375. So what this force does is it actually decreases our shear, brings it from a value to 0. It's decreasing. And then how would removing the 500 Newton force affect the support reaction at A? Right, so we look back to our moment equation. We say, how would that affect my moment equation? Because I considered that right here. So it looks like it would, right, if I took this out, then my force where did I solve for it? Right, so I use this to solve for FC, and then I use that to solve for A. So FC would be smaller, right, if we had less of a value here, and then likewise AY would be smaller. So I recommend if they give you little problems in boxes like this, do the work first, let the work speak for yourself, and you can verify that you know it. And if you get one of these wrong, you might be able to get some partial credit because you say, oh, I'm sorry, I thought since it was going from a negative value to 0, that would be increasing. You might be able to get some leeway there, but just keep that in mind when you're dealing with maximums, that it's the absolute values. All right, and so let's take a quick 5-minute break. We'll be back here at 5:42. Thanks, guys. And we'll be doing friction next. So. If you're not going to go, I'm going to go. Hey, so if there's a break, do I do anything? back. All right, so get my review stuff here. And then this, I didn't really show it. Tell us how you really feel, good or bad. I guess you can scan this. I don't know what app, but I mean, you can study union, survey, tell us how it went. All right, so during the break, I had a sort of a comment by some of my tutees that maybe this question was a little more difficult than I made it out to be. So when we get to the end, maybe, but I said we'll see how much time we have. I want to make sure I get through what I consider to be the meat of these exams, which is the inertia and the centroid. All right, so some classes are doing friction, some aren't, but I think it's important regardless. It's going to show up in your other courses, dynamics, solid mechanics, etc. Look, I guess we'll do this as a show of hands again, because we don't have too much time. I want to make sure I get to the important stuff for you guys. If you guys think this would be important to do, no? All right, so I guess mostly Zoran or Medeiros in here. All right, that's fine. So I guess it'll be available online. I'll post it afterwards. And I'll sort of have like a detailed step for the ones that I didn't go through. I'll like write little paragraphs, I guess, talking about how to do them. So we'll do this centroid one, because I like this one. So it's question 959, and I believe that's in I don't think that's in the 13th or 12th edition, so if you're trying to find it, it might be kind of difficult. But all right, so zoom in a little bit. Locate the centroid, x bar and y bar of the composite area. Right away, we see a couple shapes, right? It looks like there's a square, rectangle, triangle, and then looks like sort of a rectangle with like a quarter of a circle missing. So what I'm going to do is I'm going to go ahead and I'm going to basically count out my shapes, right? So I'm going to consider this whole bottom part to be one shape. Because when we're taking centroid, the equation that we're going to want to deal with, if we have a composite, right, composite area, is the sum of all the smaller centroids times the area over the sum of the area. And likewise for the y, right? It's just y. Okay? So I found this first area right here. I'm going to label it 1. Okay? And then my next one, I'm going to pick this triangle up. I'm going to say that's 2. And then I'm going to go ahead and say this is 3. So I'm going to continue this, right? And this is missing, but I'll just end up subtracting it at the end. So this quarter of a circle will be my 4th. So I have 4 total shapes here. And I could make more, but this I think is the least amount of shapes we can make without making it complicated. Actually, we could do 3. But we'll do 4 just because sometimes you may need to do 4, right? So 3 would be if I just did this whole sort of rectangle here and then just took out the triangle and then took out the semicircle. So when you're doing these, you're going to want to see what the fastest way would be. So the fastest way would be 3, but I'm saying phooey to that, doing 4. All right, so we'll make a little table. I like to make tables. They can help us organize our information usefully. So we're going to have our shape, right? We're going to have our little x centroid, little y centroid, and then our area, right? And then we'll have our shape 1, 2, 3, and 4. Came together pretty nice. So we'll start off with 1. All right, so I draw out my shape. And I see that it's sort of sitting at the origin, so I don't really have to worry. But these other ones will be off the origin, so we'll need to account for that. And I'll show you how. So we'll just draw like a little x, y axis. And they give us this distance here. So we have 3 plus 4, and then the radius here is 3, so that distance there. So that total distance at the bottom is 10. And some professors may give you a formula sheet that has the centroids on them for like common shapes like rectangles and triangles and such. Actually, it should. Of course, I don't have it. So rectangles are fairly easy, right? The centroid will be at half, I said it earlier, half of the base, right? And the centroid for the y will be at half of the height, right? So my height here that they give me is 3 inches. my base is 10. So with that, I can say my x centroid is 5, my y is 1.5. Okay, so I'll write that over here, 5, 1.5. And my area of a rectangle is base times height. So that's 10 times 3, or 30. And that's in square inches, right? Because it's inch times inch. Okay, so 30. So now I have my second shape, right? What's my second shape? That little triangle. So I'm going to say, okay, pretty nice triangle. So I say that's 3. That's 3. And I don't have that hypotenuse there, but I don't really need it, right? Because my centroid equations for a triangle ask me for, so for a triangle, it's 2/3 of the base from the small side, or 1/3 from the large side, right? So I'm going to go with 2/3 of the base. And then for y, it's going to be 1/3 of the height, always. Right? And so I'll draw my x and y axis here. The only thing is, it's sort of held up by this part of the shape here. So it's actually off the axes a little bit. So we're going to need to account for that when we're finding our x and y bar. Because we're not just isolating the system, right? We have to take it into account with the total system. So that distance that it's raised is this height right here, 3 inches. So we'll be adding that to our y bar, right? So plus some initial y. So 2/3 of the base, 2/3 times 3 is 2. And 1/3 of the height, 1/3 times 3 would be 1. But then we have to add that 3 inches. So we're going to say it's equal to 4 inches. Right, and my area is 1/2 base times height. So 1/2, 3 times 3, 4.5. And that's inches squared. So we're going to add that to our table. And I just like to have the table here because it's easier than like sorting through like, okay, where's my final value? There's my final value. Just everything's right there. All right, so my third shape is going to be my rectangle. Right, so I said we have a rectangle here, or a rectangle from here to here rather. Right, we're just going to subtract this little portion of our sphere, or our circle rather, because it's 2D. So my base is 4 plus 3, so it's 7. My height is still 3. All right, but where is this with respect to the origin? It's sort of shifted a little bit, right? So here's my origin. And our shape starts here, right? So I need that distance. So in that case, that's 3, and that's also 3. 3 here, 3 here. So we're going to include that in our centroid equations. So x tilde, or x squiggle, however you want to say it, 1/2 of the base, right, because we're dealing with a rectangle, plus some initial x, is going to give us 1/2 of 7, which is 3.5, plus that 3, which will be 6.5. Y squiggle, 1/2 of the height, plus some initial y value, which would be, the height is 3, so it's 1.5 plus this initial y, 3, 4.5. Okay, and then finally I have area, base times height, base 7 times height 3, 21. So I'm going to add it. 6, 4, 21. Okay? There. Zoom out a little bit. Cool. So now we have our final shape, 4. Right? So 4 is a quarter of a circle. So like I said earlier, if they're going to give you something like a quarter of a circle, I'm not sure your professor is going to require you to memorize that. So unless they specifically said so, I would expect some sort of formula sheet. And on that formula sheet, it gives us values here. It says the distance from this point to the centroid is 4r over 3 pi, where r is the radius. Let me zoom in a little bit on that. So they give us the radius is 3. And then they also say that the y is 4r over 3 pi as well. Okay? Where our r is equal to 3. Right? And this one is even further away, right? Because our x and y axes are over here. So in this case, right, we're going to have something like this. So we need this point to this point. So that height right there is 3 inches. But this distance is what? It's 7 inches, right? Because that's from here to here, right? So 4 plus 3. That's where we're starting right there. So now we have our value. So we can say that x tilde is equal to our initial, right? So our initial is it? Oh, okay. So all right. So I'm going to do it a little differently, actually. That'll make it easier. So I'm going to start from this point, since we have values from this point. I don't want to have to try to find from there. So it's 3 to here, but it's another 3 to get to this point. So I'm going to say that my initial is 6. So I'm going to go 6 and then subtract 4r over 3 pi. Right? So I'm going to go up 6 and then subtract 4r over 3 pi to get to that centroid point. Okay? Or rather, that was the x. I'm sorry, that's incorrect. So the x should be 10, right? Because it's 7 to that point and then another 3 to that point. So that's 7 plus 3 is 10 minus the 4r over 3 pi. Y squiggle is that 6 that we just talked about minus 4r over 3 pi. Yeah, that's right. Okay. And so this value here, make sure it's still on the screen. This value here is equal to, I'm gonna keep it simplified as possible, so I don't really have to work with it too much. 10 pi minus 4 over pi, right? Because you multiply by 3 pi. This is right? I did this before. So if you multiply, or you divide rather, by 3 pi. Okay, so we're good. And then that's equal to 6 pi minus 4 over 3 pi. Right? Let me just make sure. Correct, yeah. So what I'm going to do, since I was wrong in that, all right, so it's simple algebra, right? So we need a common denominator to add or subtract. So we're going to divide this by 3 pi, or we're going to multiply this by 3 pi over 3 pi, right? Or 1. So that's 3 pi times 10, which is 30 pi, minus 4r over 3 pi. Cool. And then we'll do the same thing with the 6. We'll multiply by 3 pi over 3 pi, which is 1. And then we'll do 18 pi minus 4r over 3 pi. Cool. Oh, okay, I see what I did. All right, so then our area, and they give this to us again, is equal to 1/4 pi r squared, equal to 9 pi over 4 inches squared, right? Because that's 3 times, so I just left it like that. All right, so we'll fill this in. Our x was this value right here, so that's 30 pi minus 4r over 3 pi. And then 18 pi minus 4r over 3 pi. 9 pi over 4. Cool. So it asks us to find the centroid, right? So now that we've figured out all of our shapes, we need to add or subtract them. So in this case, I'm going to be adding this, this part 1 here, adding this part 2 because it's shaded, and adding this part 3 while subtracting that part 4. Okay, so add, subtract. So we're going to do that in our sum equation. I'll try to make some space here. All right, so our x bar will be equal to, and we multiply, right? We multiply the centroid times the area, right? Because if you just added up all the centroids and then divided by the area, you wouldn't really have a clear value of, which one was larger, which one carried more meaning, right, for the centroid. So in this case, we have x bar 5, not a 50. So it's going to be 5 times 30. Plus 2 times 4.5 plus 6.5 times 21 plus, and I'm going to run out of space, of course, this times this, right? So be 30 pi minus 4r over 3 pi times 9 pi over 4. So barely enough space. And then divide by the sum of the areas. 4.5 plus 21 plus 9 pi over 4. All right. And so since I messed up on my paper here, I don't really have it solved. And that would take a little bit to plug this into your calculator, so I guess I'll leave that to you guys. But it's all set up right here. You just have to plug it in and solve. And then we'll plug it in for the y bar as well. Sorry if that's slanted. I tend to write sideways. It's a bad habit. So now we need to do our y bars, right? So we're multiplying these together. So 1.5 times 30 plus 4 times 4.5 plus 4.5 times 21 plus that thing. Minus 4r over 3 pi times 9 pi over 4. Divide that whole thing by the sum of the areas, which is, again, the same value as it was above, which will give you your y bar. So I'll put up the correct solutions later. Just work that out in your calculators. So what we did was, like I said, if it's a composite area, then we need to use this equation. And we found our centroids of all of our shapes. We found all their areas, put it into a nice little table, and simply plugged in the function. Right? So everything is given to us. We just need to find out how to sort it. All right. Yes, I'm sorry. Yep, you're 100%. Yep. So remember I said earlier we have to subtract this because it's not shaded, which of course neglected to do. So we're subtracting the 4, right? Any of our 4 values we're going to be subtracting. Thank you very much. All right, and would we subtract them from this area down here? I can't actually ask that. I mean, I can ask that, but no one can answer. So since we're neglecting it in our total area, then yes, right? Because this portion right here, this 21, takes that into account. We're taking that back out again. All right, great. So that's what we did. All right, so that's centroid. It's fairly simple, even for composite bodies when you can break them into shapes that you know how to deal with. All right. And so the next question that I want to do, those are pretty fun. So it looks like we have 30 more minutes. So I'll do this one last problem, and then we'll open up for questions and solutions. It is right here. All right, so this is a fairly common structure. You'll see this a lot in solid mechanics. It's a T-beam. Another common one is an I-beam. It's just like a little piece added on at the bottom. So it has 3 dimensions, but we're considering the 3rd dimension to be negligible, right? We're cutting it some differential value at the 3rd dimension, so we're not going to deal with it. So it says determine the moment of inertia of the beam's cross-section area about the y-axis. All right, so we have our equations. So our I, y, and then it looks like right here we have one type of shape, right? We have 2 rectangles. So IY for rectangles is 1/2 height base cubed, right? And that's something that either you can memorize. It's sort of easy. The I, it's 1/12. So you're just switching the bases and the heights. But like I said, that should be given to you. All right. So conceptual questions. What is blank? It's not there, but it should say X bar, and this should say Z bar. And we spoke earlier, we just spoke, there is no z-axis, right? Because z. So this, in this case, we can consider to be 0. We can answer that right away. All right, what is x bar? Well, we have to figure that out. I'll do the first part of the problem. 35. So I'll do this up here, and then maybe that one on this side. All right. Yeah, looks good. So I have 2 shapes. Like the last problem, I need to break shapes. It's like 1 and 2. My first shape. And they give us a height of 50 millimeters and sort of like a base of 300 millimeters. All right, and it's connected to this shape, which is also a rectangle, which has this base here of 50 millimeters, and then a height, they give it to us, of 250. Okay, so this is my first shape, this is my second shape. I'll just erase this. All right, so what I want to do is I want to find my total IY value. So what that includes is this equation right here. So my IY is height base cubed. So if I'm considering this to be my center, right? All right, that's my x. That's where my x and my y axis meet. So I need to do my equation, right? And that's, okay. So another important part is added onto this is some a, and this would be dx squared plus a dy squared. And this is if the centroid of your shape is not along the centroid of your axis, rather. It's not along the axis that you have. So in this case, our centroid of our shapes are going to be right in the middle. These are going to be our centroids, right, because we're dealing with rectangles. And they lie along the y-axis, so I don't have to include this little thing right here. It goes to 0. Okay, but if my shape was slightly shifted, I would have to include some distance multiplied by the area of the entire shape. I'd have to square that distance. But in this case, we don't have to deal with that, so we just deal with this first part, which is like I naught y, right? So if you see that in an equation, you know what it is. Okay, so the I naught y in this case is 1/12, and then it's the height, which if I'm dealing with my first, this will be my first shape, right? I have a height. Now, is it the height of this actual rectangle here, or is it the height away from our axis? So what's important to note is the moment of inertia deals with distances, right? We're dealing with shapes and areas at a distance, and it has to deal with energy. Without getting too much into it, it's about, I'll move it up a little bit, it's about energy in our system. Cool. So when I'm doing my equations, I want to make sure that I include in them the ability or the distance away from the axis about which we're looking, which in this case would be this value here. So my height of my shape itself is 50 millimeters. And then my base of the shape itself is 300 millimeters. Right, and it has a y centroid along the y-axis, so we don't include anything else. Right, and this comes to the fourth. I don't think to the fourth has a quick little name about it. But it's a fourth dimensional force. And then we have I2, right, of our second shape. Sort of our height. I didn't include it up here, but it should be cubed. Oh, we plug that in, we get a value, 2.6 times 10 to the 6. All right, and then what do? We simply just add them together. So IY is equal to IY1 plus IY2, which is equal to 115.1 times 10 to the 6th millimeter to the 4th. Okay? All right. So this is 1034. It said determine the moment of inertia of the beam's cross-sectional area about the y-axis. So we did that. Cool. The reason we're not using like height in this case, so the reason I'm not saying okay it's from the x-axis to here, is that would mean a shape that would be that large, and that we don't have that shape, right? So we're just considering a shape. We know its center is along the y-axis. That's all we really care about. And so I'll just sort of section this part off. So that was our first part of our problem, right? And so now our second part says, determine y bar, right, which locates the centroidal axis, x prime. So this right here, that's apparently where y bar is, for the cross-sectional area of the T-beam, and then find the moment of inertia about the x prime axis, right? So we just found the moment of inertia about that y-axis. So now we need to find it. We need to find the centroid, the y bar, and then find the moment of inertia about that axis there. Okay? So we need our equations, right? So our first equation is the y bar equation. This is 1035. We're good. So y bar is equal to over a, right, which includes y1 times a1 plus y2 a2 over a1 plus a2. So we're pretty much going to do this is we're going to be evaluating these structures, and now is when height matters. Now when we're looking at these little y tilde is when our height is going to matter. So our y tilde for this first shape here will be half of this height plus the initial height, right, which is 250. So our y tilde we'll do for 1, going to be in the center. And then that's 300. Y tilde is, remember this, 25 plus that 250. Our area, we got it before. Well, actually, no, we haven't gotten it yet. I'm sorry. Which is 15,000. Right, and that's squared. And so our second, right, this is centroid. I know that's 50. I'll let this, well, right here's 50. Centroid. For this shape, half of 250, right, because this is where our axis is. This is where our origin is, so it's just half of that. Base times height, because that's a rectangle. Okay. And so now we can solve our problem. Right now we have all of our variables in our equation, and so we can solve. So I'll solve it. You guys can solve it, but I'll just give you the answer. Y bar is equal to 206.82 millimeters. Okay. So now we need to find, the question asks y bar and find the moment of inertia about the y prime axis. Oh, I guess it's easier like that. So we're going to make a little table again. And so now we need to make our equation a little different, right? So it's x, this is prime, sorry. Still show, yeah. Is equal to, right, the sum of my I naught x primes, right, because I said it earlier, right, this is our I naught part of our equation, so this is our I naught part of our equation. And then here we are going to have some distance from our centroid to our centroids of our other shapes. So we're going to need to include that differential y distance. Okay, and so it's 5. So we'll do shape. And then this would be I naught x. This would be area. And this is dy squared. This is a dy squared, just to make our lives easier. Okay, so we need to sum these, right? And this would be like that, right? So it'd be the sum of all of these. In this case, we only have 2 shapes. So I want to make sure we have enough time for questions. So I gave you guys these equations already. So it's half, in this case it's the x, so it's half base height cubed, right? So fill in these values because I calculated them at home. And we found the area already for the shapes. All right, but like I said, these I naught x was solved with this portion of the equation. And then our dy. Okay, so this is where it gets a little tricky, right? So applies. So you know this drawing better. So here we have our y prime, right? So this is our axis about which we're trying to find the moment of inertia. So now what our problem is, now this differential distance comes into play. So there is a difference between our centroids here, or is there? I wrote it, but I'm not sure that there is. Okay, so we need some dy, right? So we need some distance in the y-axis. So it's some height. So our y centroid for this shape we know is here. and our y centroid for this shape is about here. So this is the distance that we're finding. That's our dy value, right? These distances between the axis and the centroid. In this case, it's the y, because that's what's given in our equation. So I found these distances, right, from here to here, because it's this centroid minus, right, so this centroid was 275, and I subtracted the y bar that we found, 206.82. And so I got, for some reason I put it, because I squared it, all right, so 4,624 square millimeters. I squared it because that's what we have to do in the equation, so I can make it easier. And then 67424 rather. Oh, I'm sorry about that, guys. 724 square millimeters. All right, and then if you just multiply 6.93 times 10 to the 7, and then multiply these two together, give you this 8.405 times 10 to the 7. Okay, so now all I need to do is sum them, right? So like this equation shows here. So you'll get eventually, if you do the summation and addition correctly, you'll get I x prime is equal to 221.58 times 10 to the 6 millimeters. Okay. All right, so that pretty much does it. So here we have what is x bar. So I can find x bar, just a little tidbit on the side. X bar we found earlier was by this equation. Right, and we didn't really do it here, but we could find our little x centroids of our shapes, and then we already have our area, so we'd be able to find our x bar. In this case, we have all of our x components of our centroids actually lies along this y-axis. So they're equal to 0 because they have no distance away from the y-axis. Therefore, the centroid is equal to 0. And you'll see that because these centroids here, they would go to 0, and then you're multiplying by 0, and then 0 over a is equal to 0, so 0. Okay, so that concludes the problem section of the study union section. I'll now open it to questions. So hands, please. Right, sure.
Question about this particular problem.
Sure.
How'd you get 275? Shouldn't it be 175? It was 150 plus 25.
Okay. So this height here, the question was, how did I get 275? So this is my initial height that I'm dealing with, right? And it's 250. I don't know if you can see that. It's 250, right? And then I have to do half of this, right? So half of this is 25. So I did 250 plus 25. All right? Cool. Any other questions?
Explain how you got dy.
dy. All right, sure. So actually, let me draw it out on paper. Might be a little easier to see. I'm going to exaggerate. All right, so we found this is our x prime, right? And that's at a height equal to our y bar, which is like 206 point something. I can actually find it. So that dy comes in where I need to find the distance from the axis that I'm finding to the axis of the center of the shape. So, excuse me. So this is where the centroid is for this shape, right? So that goes through the x in this case. So the distance from this axis to this axis is my dy value. So that height we found earlier was 275. From there to there was 275. And I subtracted 5 minus this value here, 206, to get this distance here. All right, and the same thing for below. It's this axis here, so this distance here is my dy. And so I did the y bar minus the centroid of this shape to get my dy. Cool? All right. Questions?
Going back to the truss problem.
Sure. All right.
When you did the summation of moment at C, you go over the triangle. I understand the triangle math part, but how did you know to use that to find the distances?
Okay. So you need a force times a distance. In this case, I have a perfect perpendicular distance from the point about which I'm taking my moment to the force. So if you can theoretically take any distance from your moment to your force, and it should still give you the same moment. But in this case, I did a perpendicular distance because I saw that this F was coming along, like I said, that line right here, and that's perpendicular right there. So I figured if I found this distance, I wouldn't have to worry about the x and y components. I just knew the distance in general. Cool. Viv, you look a little confused.
Yeah, I don't understand how this is makes it we don't have to find the x and the y components.
Okay, so I want to find the perpendicular distance between these two axes, right? So this is the axis of the force, and so I made an axis that's parallel to that runs through point C. So I can find a distance from any point between these two axes, right? I just chose the one that was straight, the one that was perpendicular. And so if it's perpendicular to the force, then that tells us that I'm not going to need to multiply it by anything else. I'm not going to need to add some y or x component. If I wanted to, I could have found this distance here, but that would have involved finding this component of the force as well as this component of the force, right? I would have to find the x and y component. But instead, I just found the perpendicular component and multiplied that. Does that help? Do I need to go over that again? Okay. Sure.
Can I just go back to the moment of inertia with the C shape?
Sure.
And I just want to go over how did we find the dy again?
Oh, okay. So here? Right, so we got this y bar. That was the first part of our problem. Cool? And so this is our new about which we're taking the moment. Before, we're taking the moment about this y-axis, right? And so our dy's were effectively equal to 0 because there was no distance between our y-axis and our y-centroids of our different shapes. So in this case, we do have in this case, we're looking at x, right? So we need to find our distance from our x centroids. So this I need to find the distance from the axis about which I'm taking my moment equation to the shape, right? To each individual shape. So in this case, shape 1 was this height, which I found 275 minus the y bar. And in this case, it was this distance from my x bar to the centroid of this shape. It's not exactly to scale, but we found that the centroid of this shape was 125, and this height is 206, so I know it's going to be less, right? So I did 206 minus 125. That's how I got my dy value. And then I squared them, and that's why I have dy squareds down here. Sure. Yeah.
Question about distributed loads.
Okay.
Triangles.
Sure.
So when you find the force, is it 2/3 from the point you're observing, or is it 1/3?
Okay. So the question was about distributed loads, but I guess it can be also answered. So it's about triangles, right? So if this is my origin point, then trial and error / equations will tell me that my centroid is located at, right, this is my total length. Let's say that's my total length. This right here will be 2L over 3, right? So from the small side to the large side will be 2L over 3. This will be L over 3, right, from here to here. And likewise, in my wider, all third of the height. We'll call it H. H over 3 is located. And so the same thing sort of goes for distributed loads, right? Because you're just adding forces in here. So in a distributed load, the height is sort of, it's a force. So it's not really, so you wouldn't consider the y component something that it's pushing against on that side. So it would be large side. Okay? All right, we got a few minutes, so maybe we can look at that potted plant problem if no one else has anything really they want to talk about. So I sort of went over briefly how to solve it, right? We saw that the first thing said the flower pot has a weight of 50. Determine the so what I do, then I have the only force is this force by the weight. They don't give me much else. Oh, I'm not sure if I remember, do you remember the question exactly that you had about this question, this problem? Like, was it just how to solve it, or was it like something in particular about the problem? Just how to solve, okay. So what I did here, I guess I'll just show you guys this, was I found my points, right, and then I found my vectors. So I found my unit vector O to A, and then I found my position vector O to B, right, from this point to this point. I found my unit vector O to B, and then I said that my moment O to A was equal to the unit vector of O to A, dotted with the moment about point O. Right, so that's where it is here, OA dotted with unit vector of O to B, crossed with my weight, because that's my only force in this equation, right? So it's R cross F. In this case, my F is my weight. So I set up my matrix, and I don't know if you guys know this, but this is most of your matrices, or actually all of them, are 3 by 3, but maybe you might not evaluate them like that. So you might be used to seeing something like, right, where you have like an I, a J, and a K. Right, so you have some I and J and K here, and then you'll have some value, and then you'll say the first part will be, all right, so I cover this, and I cross here, subtract here. But what you're actually doing is multiplying by this constant here. So that's what I did. So I just included it in my unit vector, because here our unit vectors are 1, 1, 1. Right, that's what the I say. This is basically 1, 1. So multiplying that by 1 in my x direction, that by 1 in my y, that by 1 in my k. Here I already knew I had to dot it with this specific unit vector. So I did 0, 4 over 5, and 3 over 5. All right, so I did cover this, and I say this, right? 5.714 times negative 50 times 0, minus 1.5 and 0, blah, blah, blah. So that goes to 0, right? So I cross this one out and multiply by 4 over 5, and then negative, just mentioned. I say 3.299 times negative 50 minus 1.5 times 0. So I have some value here, and that's where my moment ends up being in the J, because then I'll cover this, 3.5 times, that's going to be 0, right? Because those are both multiplied by 0. So my component ends up being only in the J. And that makes sense because we're crossing, this is a K, right? So this is a K vector. So anything I cross with it, right? So in this case, I'm only using X components, right? So this is an X, this is a Y, this is a Z. So this 3.229 is in the X, right? So I'm crossing X, or I'm mixing up my I, right? X is the I. Give me, right? Likewise, if I crossed J and K, it would give me I, right? So if you cross two vectors, you get the third. All right, and then from there, it was sort of simple. I said the second part of the problem said that we had a maximum moment of 150. So I set the moment equal to 150, and then I set up the same matrix that we had down here. Right, the only thing that was different was the W, right? We were given this value here, but we're not given the W. We have to find it. So I just plug in a dummy variable W, and I do the same thing. I come through with my, my matrix. I solve it, and then I get this equation here, and then I can solve for my W. Okay? Cool. Yeah, so the important thing is if they want it about a specific axis, you're going to have to dot it with that axis. And if they say magnitude, that means scalar. If they want like a direction, that means a vector. So if you don't get your answer like that, then you know something's wrong. And if there are no more questions, any last little things you guys have been thinking about? Yeah, sure. Oh, boom. Yeah, so I'll upload this tonight after when I get home, and I'll fix any of the mistakes that I realized I made here. But if that's it, thank you guys for showing up, and good luck on finals.